Hello. Consider a string whose ends are fixed, such as the ones of a guitar or any instrument of string. Because the ends are fixed and cannot move, if you pick the string, it will vibrate, but will do so satisfying that the ends remain fixed. This imposes a certain restriction to the allowed vibrations for that string. If you have a sinusoidal wave, only waves for which the length of the string is a multiple of the wave's wavelength are going to be permitted. When the strings of my guitar vibrate, they produce sound at the frequency the strings are vibrating. Therefore, the pitch will depend on the length of the string. That is why, when I place my fingers at different positions, I am shortening the length of the strings and changing the pitch of the sound from that string. The frequencies at which each string can vibrate is limited by these frequencies are basically a fundamental one and harmonics of this fundamental frequency. Remember that we saw that the speed of the wave depends on the tension on the string and its mass density. I can change the speed of the wave by applying more tension to the string. Because the speed is the wavelength times the frequency, given that the wavelength is set by the length of the string, changing the tension changes the frequency also, the pitch. That is what I do when I tune my guitar. Also, the mass density affects the velocity of the wave, and then also the frequency. That is why the material of each string is different to help give the right pitch. The harp, for example, also plays with the lengths of the strings to get a broad spectrum of sounds. These waves are standing waves. They have fixed ends. They are waves that seem not to travel. We can write them as a wave traveling from one end that bounces back when it reaches the other end. The return wave has the same frequency as the first one and the same amplitude. Let's look at the math behind this. This is the equation for a wave moving to the right. And this is the equation for the return wave moving to the left. If we sum both waves, for that we will use this trigonometric identity. So this sum is so the amplitude of the resulting wave is twice that of the original one. There is still a sinusoidal behavior in the time with frequency omega. But we have this sine term that depends on the position. This term multiplies the whole wave. This term can be thought of as the amplitude that is being oscillating from a value of 2a to a value of 0, depending on the x position. But if you look at the sine term, we know that the sine is 0 for x values of 0, lambda over 2, lambda, 3 lambda over 2, and so on. So for those positions the amplitude is zero, no matter the moment in time. There the wave will always be zero. These are the nodes of the wave. For the rest of the points, the amplitude will be different from zero, and the motion of the string will be oscillatory with more or less amplitude depending on the x position. We have a standing wave where the nodes are fixed points. These are the only allowed waves in a string whose ends are fixed. Those are the oscillations of the strings in my guitar and of any string instrument. Standing waves can also be found in microwave ovens. In that case, they are electromagnetic waves, electromagnetic standing waves. Right at the points where the amplitude gets maximum, the molecules of water inside of the oven oscillate the maximum, and this heats the water or the food that you have inside. This also happens for wind instruments, that you have a tube and you have some standing waves inside of it.